So, thank you everybody for joining this second lecture of the course on the mechanical modeling of curved and twisted beams, a geometrically exact approach. And this is the second lecture of this course. And I will start summarizing the main results of the previous lecture by Professor Cazzani at the University of Cagliari, because I know that there are a few people who were not present yesterday, who could not attend yesterday. So I will summarize the main findings, which are the pillars of the theory that we will discuss during these lectures. And next, I will move to the specific topic of this class of today. So I will share the textbook we are using, and I will show you the main results that we obtained that Antonio Cazzani presented yet.
Non sta condividendo lo schermo.
Sì, sì, ora. So, yes, I will need to share my screen. Okay. So now I think you are able to see my screen. I think so. Is that true, Valentina? I know one of the attendants is my PhD student, so I know her.
Yes.
So Valentina is.
Yes.
You can see my screen.
I can see your screen. Yeah.
So basically, yesterday we presented the model of a curved beam and also explained some basic results. And the starting point was this some elements of differential geometry, which are related to the mainly to the axis line of the beams that we will study. So the axis line is supposed to be a smooth curve of the three-dimensional space in general. It can be planar or also as twisted or non-planar. And we started by describing the triad or the triplet of the base vectors that we associate to this line. So if you want to look at the figure, there is a line, a smooth line in the three-dimensional space, and we are attaching a triplet of unit vectors to this line, which is composed of three mutual orthogonal vectors. So we have a system of orthogonal coordinates associated with this line. And the first vector that we introduced is obviously I won't go through the details of the demonstrations of the mathematical results that were presented by Antonio yesterday. I will just summarize the results. So the first vector, which is E3, as the index 3, but it's the first vector we introduce, is just the derivative of the position vector of the generic point with respect to the arc length, the abscissa or the arc length measured along the curve alpha. So this vector is a unit vector because it's the parameterization that we are choosing is exactly the arc length. So in the limit, the vector dx has a norm that is equal to ds, and the vector is tangent to the axis to this axis line alpha. So this is the first vector of the triplet that we will diffusely use during the course. The second vector, the second and third vector, I won't go through the details because this is not necessary. I will just present the final formula that we introduced, which are the Prené formula, and the drawing that illustrates the other two vectors. So the first vector, even is labeled E3 is the tangent vector. Then we have other two vectors which are both normal to the curve, but one is the principal normal, or E2, vector, which is basically defined as the second derivative normalized at the second derivative of the position vector with respect to the arc length alpha. So it's the second derivative of x with respect to s squared divided by the norm of this derivative. And the third vector is E1, is just defined as the vector product of E2 and E3. And so that is unit vector and normal to both E2 and E3. And this other vector is named the binormal or the binormal vector. We have three planes, the osculating plane, which is the plane that contains E2 and E3. We have the normal plane, which contains E2 and E1, and we have the rectificante, I don't know exactly, a rectifying, I suppose, plane, which is the one that is a fixed plane when the curve is planar, when this alpha curve is planar, while changes when the curve is twisted as is not contained in a single plane. So with these preliminaries, and Antonio yesterday presented the main point of the analysis, that the differential geometry analysis that we will use, the main results, which are the Frenet formula. So the Frenet formula are summarized here and by these three equations. And they can be also assumed as the definition of the two parameters, which are the curvature and the torsion of the curve alpha. So they give the Frenet formula give the derivatives of these basic vectors, the E1, E2, and 3 with the arc length s. So the derivative of the first vector, which is the binormal vector with respect to the s, is directed as E2, and it should be pointed out that the derivative of a unit vector is always orthogonal to the vector. This has been demonstrated by Antonio yesterday. So all those derivatives give vectors that are orthogonal to the vector that we are differentiating. So this because these vectors are unit vectors, so one can demonstrate the derivative of a vector with fixed length, which is the case of a unit vector, is orthogonal to the vector. And so the E1 over ds, so the derivative of the binormal, is 1 over tau E2. And this is because when, as I said, if the rectifying plane is fixed, we have a planar curve. When the rectifying plane changes, then we have a torsion of the curve. So a curvature of second notion of curvature, and which is defined by this formula. Basically, you can take tau as defined by this formula. So the derivative E1 over ds is E2 divided by tau. Then, because the derivative of a unit vector is orthogonal to the vector, but it's not necessarily a unit vector. So this is the case. The derivative of the E1 over ds is not a unit vector, and so there is the scale factor 1 over tau appearing, and this 1 over tau is the torsion. While the derivative of E2 has two terms. One is directed as E1 and has the minus sign and the scalar, the coefficient 1 over tau. And the second term is directed as E3, minus 1, and the coefficient of linear combination is minus 1 over r, rho, minus 1 over rho. The third one is It's more simple. The E3 over ds is so the derivative of the tangent vector is 1 over rho E2. So basically, if we look at the first and the third formula, they speak clearly. So this curve has two curvatures, one in a plane, one out of plane. If the tangent vector changes with the arc length, if we have an in plane, in the osculating plane, curvature, radius of curvature, rho, and 1 over rho is the curvature, rho is the radius of curvature. So basically, if the curve has no curvature in the plane, this d3 over ds will be 0. So if rho is equal to infinity, we have 1 rho equal to 0, and we have the trivial case of a straight line. On the other hand, if the vector E1, the binormal, doesn't change with the arc length, we have a planar curve, and the tau is infinite, which means that 1 over tau is 0. While more involved is the derivative of the E2, which is the normal, the principal normal vector, which has components both on E1 and on E3. This is the main result of the differential geometry of the curve alpha that we have used yesterday. Next, Antonio has presented our basic assumption about the displacement field that is exhibited by the beams that we are analyzing. We assume the classical beam theory in infinitesimal strains, and so the displacement field is given by component v or function of s or x3 that we call both either s or x3, the arc length along the axis line, and then a vector product of a rotation vector phi times the position vector in the plane of the cross section, which is the element orthogonal, the planar surface that generates the curved beam, and which is orthogonal for alpha. So this y minus x gives y is the position vector of the generic point of the beam, while x is the position vector of the centroid of the section of the same section. So y minus x gives r, the position vector relative to the centroid of the cross. This is the main assumption that we are assuming. So we are assuming that we assume about the displacement field of the beam. So we assume that it's a composition of translation of the cross section u equal to v plus an infinitesimal rotation about the centroid. So assuming this displacement field, Antonio showed yesterday, first of all, since now we have in the end we are working with a three-dimensional object, which is our curved beam, and this three-dimensional object has is described. So if we think to the beam and not to the axis line alpha, but to this three-dimensional object, which is created by the motion of a planar figure, which is the cross section, when its center, its centroid moves along the axis line. If we think to this three-dimensional object, which is the curved beam, we can differentiate now the position vector y of a generic point of this beam with respect to x1, x2, and x3 that we are assuming as curvilinear coordinates in the end. So these three derivatives gives the what is called in differential geometry of curves the natural basis associated to this three coordinates x1, x2, and x3, which is the arc length. So this G1, G2, and G3 are not E1, E2, and 3 because now we are taking derivatives to the position vector of a point of the beam and not a point of the axis line. Indeed, the G3 vector is not G1 and G2 coincide with E1 and E2, while G3 it does not coincide with E3 unless we are on the central on the axis line. If you are on the axis line, which x1 and x2 are 0, we have the G3 is equal to E3. While if we are in a point and it's not a centroid, the G3, which is this the derivative of the position vector with respect to the curvilinear axis or curvilinear axis or the arc length, is not equal to E3. It's a combination of E1, E2, and E3. So now, if we have these three base vectors which are associated to the beam, so basically those are the three base vectors associated to the beam, while E1, E2, and 3 are base vectors associated to the axis line, we can introduce the gradient of the displacement field that we have shown before. This gradient is obtained by basically when we apply this gradient to these three base vectors, G1, G2, and G3, we are basically those three relations define the gradient of U. The gradient of U is the tensor, the second or the tensor that applied to these three base vectors, G1, G2, G3, gives the derivatives of the displacement field, the directional derivatives of the displacement field with respect to x1, x2, and x3. So we take derivatives and we have that we obtain the three expressions that are given here of these three vectors which define the gradient of U. So this is an operational definition of the gradient of U. We show how this tensor acts on three base vectors, and so since any other vector can be defined as a combination of G1, G2, and G3, we are basically defining how gradient of U acts on each vector of the three-dimensional space. So we can basically the first two relations are the same as those one can derive for a curve for a straight beam, for example. But the third one is different. So we have the terms with the tau and the rho, which account for the fact that the beam is not straight line, it's not straight. And so these derivatives are simply obtained by differentiating the U with respect to x1, x2, and x3, and accounting for a finite formula. Because when we take the derivative of U with respect to x1 and x2, x3, we have to differentiate V and V, which are a function of x3, and we also have to differentiate E1 and E2 that are a function of x3, while those derivatives do not appear in a straight beam, in the theory of the straight beam, for the simple reason that the triplet that we use in a straight beam does not vary with the axis along the axis line. So these are the expressions of the three vectors that define the gradient of U. So we define how this gradient of U applies to these three vectors. Then we can also obtain how the gradient of U acts on E1 and E2 and E3, which are not G1, G2, and G3, are basically E1, E2, and 3 are the direction of G1, G2, and G3 along the axis line. And so if we want to the relations that are the expressions of the vectors that are obtained by applying gradient U to E1, 2, and 3, we have to obtain E1 and E2 are simply G1 and G2, so there is it's a simple task to obtain these to the first two formulas. While the third one, since from this equation that define G3, we can basically invert this equation and obtain E3 as a function of G3, and this is what has been done here. And now we can compute the gradient of U applied to E3, obtaining this formula. Okay, so also in this formula that that Antonio has presented yesterday, we can recognize that there is, first of all, there is a factor in front that is depends on the curvature. If rho is equal to infinity, this will be 1, but otherwise it will not be 1. It's the Jacobian of the transformation from curvilinear coordinates to Cartesian coordinates. And in the brackets we have the also terms that are associated with the curvature of the beam. So this equation is not simply is not the same as the analogous equation in a straight beam. So why we have done all this machinery? Because the derivatives of the displacement field with respect to x1, x2, and x3 are not the expression of gradient we applied to E1, E2, and E3, but are differently the vectors that are obtained applying gradient view at G1, G2, and G3. So we first compute these three vectors, and then we pass to the vectors that gradient view associates to E1, E2, and 3 for this reason. While now, if we have the definition of the gradient view, we know that the strain tensor of the beam, if we regard the beam as a three-dimensional body, the infinitesimal strain tensor is given by the summation of gradient u and the transpose of gradient u. And so, by if we want now the components of epsilon, this infinitesimal strain tensor, in the basis of the Frenet basis, we use the definition of gradient view, the transpose, and the property of the transpose of a tensor, and we obtain this general formula that has been expanded in components, and we have the only three components of epsilon that are not zero are epsilon 1, 3, epsilon 2, 3, and epsilon 3, 3. The first two equations give deformation chart related to the change of angles between the direction 1, 3 and 2, 3. So those are the shear strains. So associated with the change of angles between the direction 1 and 3 and 2 and 3. The third one is just the axial strain over the axis line. In these expressions, we can recognize in the end, if we don't, if we leave in this form without expanding the derivatives of the vectors E and T in components, we can see that basically those three relations are the same as in the analogous ones in a straight beam, but with this factor in front, which is this Jacobian rho over rho minus x2. And these are the three components. The other components are zero because we are assuming rigid displacement field of the cross section, which implies that epsilon 1, 1, epsilon 2, 2, and epsilon 1, 2 are zero. So maybe this definition of the curved beam, the final expression of this nodes will be placed before the expression, the displacement that we have given before. But we can give we can recall the definition of a curved beam, and the main result they've been presented before. So the curved beam is the solid, the 3D solid that is generated by the motion of a domain, a planar domain that defines the cross section of the beam, while its center of mass or centroid moves along this axis line alpha. And we recall the Frenet formula, and we have even some basic definitions of the lateral surface, which is the mantle of the beam delta L, and the terminal basis, the axis line, the base vectors that define the beam. Then Antonio yesterday, here really I will be fast, define the equilibrium equations of the beam by using the principal virtual work and the expression of the displacement we have presented earlier. And so by expanding the principal virtual work, by writing the principal virtual work of the 3D continuum mechanics for the displacement field that we are using, we are assuming, we obtain a one-dimensional expression of the principal virtual work, and we obtain both we obtain. So this has we obtain the equilibrium, the differential equilibrium equations of the beam. So I won't go through the details. I just want to summarize two results that have been presented yesterday. So in expanding, in writing the virtual work of the beam, we needed the volume, the infinitesimal, an expression of the differential of volume of the beam. So the differential of volume of a parallelepiped or a straight beam is very simple. It's just given if you use Cartesian coordinates, it's just the x1 times the x2 times the x3. But this is not true in the curved beam because we have a curved geometry, and so by introducing the differentials of the position vector of y or a generic point of the beam with respect to x1, x2, and x3, we can compute the infinitesimal volume through this mixed product of the three derivatives of y with respect to x1, x2, and x3, and recalling the definition of these vectors, which are the base vectors associated with these coordinates, we obtained this expression of the infinitesimal volume of the beam. So you can see that this differential, this volume is given by the S, which is the x3, times the differential of the area of the cross section, which is the x1, the x2. So, but in front there is J, the Jacobian, which is 1 minus x2 over rho. We have seen this quantity even earlier, or rho minus x2 over rho, which is the same. And so the infinitesimal volume of the beam is J times the S, the sigma. And this is also true along the lateral surface. So this is the main result I want to summarize. And then I won't go through the details, but you can demonstrate the passages or the elementary passages by going through the notes. In terms of the internal virtual work, we have obtained this expression by multiplying the three-dimensional stress tensor by the infinitesimal strain tensor of a virtual displacement that we can give to the beam, and we have obtained quite this we have expanded this product and using the expression of the infinitesimal strain vector that we have seen before and the gradient of u that we have seen before. So in the end, the equation that Antonio has presented yesterday are not very much different. So through this machinery, basically we obtain the differential equation that you can demonstrate going through the notes. The differential equation in a vector form of the curved beam are exactly the same as those of the straight beam. So we have the classical differential equilibrium equation, then nu over ds plus q equal to 0 is the equilibrium equation, the translational equilibrium equation. And nu is basically it's the resultant, the stress resultant. So it's the integral of the stress vector over the cross section of the beam. So it's as a vector, as a component, the axial force and the shear forces, the vector that corresponds to the integral of the surface tension over the cross section, and Q is just the vector of the loads per unit length. While the second equilibrium equation is the classical equilibrium equation, also valid for straight beams. The mu is the vector of the first order moments of the stresses with respect to the centroid, which has components given by the bending moments M1 and M3, and the torque, the torsional moment or the torque M3, mu3, and the mu over ds minus nu over time vector E3 plus C. C is the vector of the distributed couples per unit length is equal to 0. Those equations are the same as of those of a straight beam. But we will see that then when we write these equations in a scalar form, they are markedly different from those of the straight beam. And we have the classical natural and forced boundary conditions, which impose either the displacements or the stress results on the stress of the moment, resultant moment, equal to prescribed values on the end sections of on the end points of the axis line. And Antonio has also presented the scalar form of this equation, which is more cumbersome than the previous one. And because so the problem is that here we have a derivative of nu with respect to s. And now when we take we expand this derivative into components, we have to differentiate both the components, nu and the base vectors, because this triplet, this triad of the Frenet vectors changes along the axis line. So by taking these derivatives, we have to take the derivatives of the components and the derivatives of the base vectors. And the same happens for the derivative of mu with respect to s. So we end up with these equilibrium equations. And so you see that as compared to the equilibrium equations of the straight beam, now we have the classical terms, and we have additional terms that are associated with the curvature and the torsion of the axis line. So, for example, in the equilibrium in the one direction, we have also the shear force in the second direction, in the two direction that appears with the tau, the curvature as a scale factor, and then also in the derivative of the second equilibrium equation, and most important in the third equilibrium equation, the one with the axis related to the axial force, we see that there is also a shear force appearing in the in the third equilibrium equation. So we understand there is also the expression of the other scalar equilibrium equations in terms of resultant moments. And also in this case, we have classical terms of the straight beam and plus additional terms related to the curvature and the torsion of the axis. Right? And so this makes it clear that in curved beams, the extensional problem, the axial problem, the bending problem of a beam cannot be separated. So in a straight beam, we have that the problem of the axial force is linked, is coupled to the problem of to the bending problem, the problem with associated with shear forces and the bending moments. While in the straight beam, the only coupling is between shear forces and bending moments. Here, in the straight beam, in the curved beam, all the axial forces and the bending moments are coupled, and so we have this result that we have a coupling between the bending problems and the extensional problem. But this is not a bad it's not a bad thing in the end, because this is the reason why curved beams are being used for years, for centuries. Because if we look at the first two equations, we see that in the equation with Q2, if Q2 is the load that acts on the normal to the tangent line. So it's a normal, it's a vector that is perpendicular to the axis line. And we see that we can equilibrate a transverse load with an axial force, which is M3. So if we can have a special case in which the transverse load is equilibrated by an axial load, which is not possible in straight beams. In straight beams, in order to equilibrate a transverse load, you need necessarily shear forces and bending moments. While here, you can equilibrate a transverse force with axial forces, and this gives this is why the Romans have invented the arch, so that one can carry the transverse load through axial forces. And this coupling is beneficial because gives the possibility to equilibrate a transverse load through axial forces. And obviously, it gives some problems in terms of because more generally, you have all the forces are the generalized stresses or for axial and shear forces and bending and moments and torsion and torque are coupled. So we have more the equations are all coupled, and this will give problems in the applications. And we will see tomorrow and the day after that how we can solve this problem. But then this problem, these equations in a practical examples. But it should be remarked that this complication due to the fact that the base vectors change along the axis line is actually beneficial because it gives a possibility to equilibrate transverse load to axial forces, and this is, as we know, important in many technical problems. Another results that we obtained yesterday are through the expression of the internal virtual work. We obtain also the expression of the quantities that are the duals of the nu and m. So the generalized strains, nu and m, the components of nu and m of the resultant force and the resultant moments give the generalized stresses, and the quantities that multiply those generalized stress in the internal virtual work are the generalized, can be interpreted as generalized strains. And so in what we have seen yesterday is that the quantities that are associated to the axial forces, shear forces, bending moments in the torque are those 6 quantities: epsilon, epsilon 1, 2, 3, 4, 5, and 6, which are components, which are quantities that have expressions more involved as compared to the counterparts relative to the straight beams. So we have epsilon 1, 2, and 3. With epsilon 1 and epsilon 2 are the shear strains of the beam. Epsilon 3 is the axial strain. And these two, we see that epsilon 1 and epsilon 2 have terms that are associated also to the curvature and the torsion of the beam as a opposed to the case of the straight beam. Also, the epsilon 3 has a component that is as a term that's related to the curvature, P2. And these are epsilon 4 and epsilon 5 are the two bending strains that are related to the derivative of the vector F components F phi 1 and phi 2, plus some terms related to torsion and curvature. And finally, we have also the torsion strain, which has also a term due to the linked to the curvature of the axis line. And so what we can observe in the end, in this way, I'm sorry for the ones who have already listened to the lesson of yesterday. We have 4 or 5 students which who were not present yesterday, so that's why I summarized these results to let them follow what we will present in the following. And so, what is the main message that those equations give us? In terms of the scalar expressions of the equilibrium equation, we already said that there are some couplings that appear due to the curvature and the torsion of the axis lines. And what in terms of generalized strains? Also, in this case, we see that there are some couplings. For example, one coupling is this one. So we have that usually in a straight beam, the axial strain is related only to the axial displacement. So the axial strain is associated with the variation of the axial displacement along the axis line of the beam. While now we have in a curved beam, we have that the axial strain is also related to V2, to the transverse displacement. So this is, but this coupling is scaled by 1 over rho. So this means that if we have if rho goes to infinity, this coupling disappears. While if we have if we don't have rho doesn't go to infinity, this coupling is left. And this also explains why in these expressions of those are basically we would define these equations are the compatibility equations of the beam. So the equations give the generalized strains as a function of the displacements. We have we observe that those couplings in particular give us the possibility to explain why, for example, also in straight beams, when we analyze large displacements of straight beams, we observe a coupling between bending and axial force. because when you have large displacement, you can analyze a finite displacement of a straight beam into steps, into intermediate steps. You can split, you can break this deformation into steps. What you will have is that if you divide the finite deformation process of a straight beam into steps, in the steps that are full of the first one, you will have the axis, the axis line will be curved because of the result of the because in a straight beam, if you apply a transverse load, you have the beams presents a deflection of the displacement field. So in the subsequent steps of this process, you need to analyze necessarily. You need to analyze the deformation using the theory of a curved beam. It's not possible to use the theory of the straight beam, and so this explains that even in if you have for example, if you have a straight beam, you apply a large transverse displacements, you will feel that a reaction that the axial force will actually contribute to resist to the vertical load, because this coupling will appear due to the fact that in the process, in the deformation process, the beam transforms into a curved beam. So this is the summary. I'm sorry if I had to go through this repetition, but there are actually 4 or 5 of my students who were not present yesterday because they were busy in another event in Salerno that we could not miss, and so it was an official event of the department, and so I went through this summary of the previous lecture, but obviously, while yesterday Antonio had to give had to carry out all the passages, today I could have more fun, just telling, commenting the results. The hard job that Antonio has to carry out yesterday was more lucky, but I will have my difficult part in the second part of the lecture, so I could basically just summarize the results and the meaning, the mechanical meaning of the results that were carried out yesterday by Antonio. I think that, as in the case of yesterday, maybe we can take 10 minutes break. So because then we switch to the following topic, and so we can basically, if we have this 10-minute break, we can meet again at 4:05 for you that are connected from remote. Okay. So see you in short. Thank you.